Welcome to Visual Algebra Lecture 3.3, Cosets. By now, you've surely noticed that Cayley graphs have a certain structural regularity. In particular, if a subgroup consists of a fragment, then that pattern permeates throughout the graph. These identical copies of the subgroup are called cosets. Subgroups have both left and right cosets, which have both algebraic and visual interpretations. The left cosets partition the group, as do the right cosets, but these partitions may be different. The fact that the cosets partition a group leads to the basic property that the order of a subgroup must divide the order of the group. We'll explore these things and more in this lecture, which starts right now. By the regularity property of Cayley graphs, identical copies of the fragment that corresponds to a subgroup appears throughout the graph. You've surely noticed this before. Here's a subgroup generated by F, and here's that little fragment, and that appears elsewhere. Of course, only one of these is actually a subgroup. The other three don't contain the identity. These are called left cosets of the subgroup H. Here's an informal definition. The formal definition will come up next. To find the left coset, XH in a Cayley graph, X is an element, H is a subgroup, carry out the following steps. First, starting from the identity node, follow a path to get to X. I like to say follow the X path, or you can just start at node X. And then, from X, follow all H paths. Let me explain what I mean by that. So, this notation is meant to be interpreted as reading left to right. First, follow X, and then do everything in H. So up here, for this coset RH, first follow the R path, and then do all of the paths in H. And what is H? H is what you get by following the blue arrows. In this case, it's pretty simple. So first do R, then all the H paths. Over here, first do R squared, then do the H paths. And over here, first do R cubed, and then do the H paths. Notice that the subgroup is a coset as well. You can think of this as 1 times H. Here's a formal algebraic definition. If H is a subgroup of G, then a left coset, denoted XH for some element X, is a set of all products of the form X times little h, where little h is in the subgroup H. The particular X we use is called the representative. And similarly, we can define a right coset by putting X on the right. So HX is the set of all products of the form little hx, where little h ranges over everything in big H. Let's look at the right cosets of the same subgroup H in D4. So here it is. Now the notation is meant to suggest that we are reading right to left. So we first follow all H paths. That means go to these two nodes, and then from those we follow the X path. So this is H, or H times the identity. This is the coset HR. From the nodes in H, follow R. So R from 1 takes us up here, from F takes us down here. If you do HR squared, so doing R squared from each node in H, R squared takes you over here, from 1, and from F it takes you right there. And then finally H R cubed. If you do R cubed from 1, you get to R cubed, and R cubed from F, you get to RF. So notice that the left cosets and the right cosets of this group are different. Well, two of them are the same. This is the same, and that's the same. But two of them are different. We'll come back to that. Let's explore this in a little more detail and compare left and right cosets. The left coset, RH, means first traverse the R path and then traverse all H paths. Whereas the right coset means first traverse all H paths and then traverse the R path. So RH means first do R, then do the H paths. Whereas HR means first do the H paths, and from there do the R paths. You see how you get a different result. Algebraically, this means multiply R on the left by the two elements in H, which gives us R and RF. And notice that that's the same thing if we had multiplied by the two elements, or if we had multiplied these two elements by RF. So if we had first done RF to get here, and then we do the H paths, well, we don't get anywhere different. That makes sense visually, and algebraically, RF times these two elements is these two elements. So a coset can have multiple representatives. And hopefully it's believable which representatives give you the same coset. Given a coset, it doesn't matter where we start in here. As long as we do the H paths, we will end up to the same set of nodes. Let's look at the right cosets now, or this right coset. So HR means right multiply everything by R. So we get R and R cubed F. And similarly, that's the same as if we had right multiplied by R cubed F. Note that left cosets look like copies of the subgroup scattered throughout the diagram, whereas right cosets are usually scattered because we've adopted the convention that arrows in a Cayley graph represent right multiplication. In other words, we are reading from left to right. If we had done the opposite and read from right to left, then it would have been the right cosets that look like copies of the subgroup and the left cosets that don't. A key point is left and right cosets are generally different, and that's going to be important going forward. Let's take a few moments to pause and compare the left and right cosets of that subgroup H in D4. And I want to ask you, what sort of things do you notice? So here are the left cosets up here, and the right cosets are down here. What do you think are properties of cosets that we might be able to prove? Well, one thing is that they partition the group, both the left and the right cosets. And that should make sense because you can think of a coset as starting from a node and then following all of the paths in the subgroup. So if you have any node in the Cayley graph, you can just start there and follow, and there's your coset. Also notice that these have the same size. This is true for left cosets and right cosets. So this is something that we will be able to prove, namely that all cosets have the same size and that they partition the group. As a corollary of that, it means that the size of a subgroup is going to divide the size of the group because we can divide up the group into cosets of equal size. Let's now look at the left and right cosets of a different subgroup of D4, namely N, which is generated by R. The left coset Fn in D4 is what you get by first traversing the F path and then traversing all N paths. So the F path means just go to F, and then all paths in N mean follow all red arrows, and this is what you get. In contrast, the right coset NF means first traverse all N paths, so first do those red arrows, and then from each node traverse the F path, and that leads us inward. And notice in this case we get the same 4 nodes. It's the 4 reflections. Algebraically, F times N is the product of F times each of the rotations, and so you get all 4 reflections. Whereas NF is the product of first those rotations and then times F, and so you still get those 4 rotations. Just notice that the order that these are in are different. So they get shuffled up a little bit. Also notice that there are multiple representatives of the same coset. I mentioned this earlier. So Fn is the same as Rfn, which is the same as R squared Fn or R cubed Fn. In other words, over here, it doesn't matter whether you start at F or any of these other nodes in the coset. From any of them, if you follow all N paths, you will get back all of them. Analogously, for right cosets, it doesn't matter which node that you do after the end paths. So this is a little bit less clear, but hopefully it's believable that NF will get you in here, and RF means from each of these do red, blue, and then R squared F means from each of these nodes do red, red, blue, and then R cubed F, all four of these representatives define the same coset. For this particular subgroup, each left coset, now there's only two of them, there's the subgroup itself. Remember that N is equal to 1 times N, and that's the left coset, and then N is also equal to N times 1. So that's the other coset, the other right coset. So in both cases, each left coset is a right coset, and when that happens, such a subgroup is called normal. That's why I use the word N to denote it instead of H. Let's now state and prove a proposition that we observed from the Cayley graph, which is each left coset can have multiple representatives, but in particular, if B is within the coset AH, then A and B define the same left coset, so AH equals BH. To prove this, we just use the definition. Since B is in AH, that means, by definition, we can write it as A times little h for some element in H. In other words, H can be written as A inverse B, and A can be written as B H inverse. Again, I'm just using this equation. I can solve for A, and I can solve for H. And at this point, it's not clear if we're going to need or use one or both of these, but let's write them down so we can see them. Okay, so what are we trying to prove? This is our assumption. B is A times H, and we're trying to show that AH equals BH as cosets. So to show the equality of sets, we typically need to show both containments, that AH is a subset of BH and also a superset of BH. We can do this by taking an element in AH and showing it's in BH, and then take an element in BH and show it's in AH. For the first, let's take an arbitrary element in AH. Let's call it AH1. So H1 is some unknown element in H. To verify this, we need to somehow write that as B times something in H. So BH2, say, for some element H2. So how are we going to find an H2? Well, there's not much to work with. We really just have these equations involving B, A, and H. So what if we take AH1 and we make this substitution and write that as B H inverse, that's times H1, and now we have B times something in H. So here that is formally. AH1 is B H inverse H1, and of course this is in H because H is a subgroup. The converse is similar. Let's now pick an element in BH. Let's call it BH3, because that's the definition of what this coset is. Now we need to write this as A. We need to show it's in AH. So we have to write it as A times some other element in H. Let's call that H4. It might be the same as A3 or A2, but we can't guarantee that. How do you think we're going to do that? Well, we need to take this and write it starting with A. And fortunately, we can do that by the substitution. Plug AH into here. So BH3 is AH times H3, which is A times AH3. And once again, that is in H by closure. And so this element is in the coset AH. And that's all we had to do. Now we have equality of these cosets. Here's a corollary. That's very boring, but it's extremely useful. We will refer to this throughout the course. And I don't have a name for this. Some very straightforward results have names like Lagrange's theorem or Cayley's theorem, but this doesn't. So I've been calling it the boring but useful coset lemma. And if you have anything else better than that, let me know. I have another few months or maybe up to a year before I send in the final draft of my book, and I would love a better name than the boring but useful coset lemma. So this says that the equality, or the coset xh equals h, if and only if x is actually in h itself. And analogously, the same thing holds for right cosets. Let's now write a formal proof of something that we observed by inspection earlier, namely for any subgroup H, the left cosets of H partition the group G. And the same proof is going to work for right cosets, basically just hold it in a mirror. Now let me say what I mean by partition. So we have a group G like this, and we have a subgroup H. And I mean, the left cosets fill up everything in the group. So every element, little g, is going to lie in a left coset, GH. But also, it's only going to lie in one of them. It lies in a unique coset. We don't ever have anything like that. Here's the proof. The first part is motivated by the diagram that I just showed you. If we take an arbitrary element, G in big G, then that will lie in a left coset, namely the one GH. What about uniqueness? Well, we just showed that if G lies in a coset KH, then KH equals GH. We just proved that in the previous slide. And that establishes uniqueness. Here's another proposition that we observed from the picture, but we still have to prove formally. That is, all left cosets of H have the same size. How are we going to prove this? Well, first, it suffices to show that every left coset has the same size as the original subgroup H, because that is a left coset. And how do we show that two sets are the same size? Well, one way is to construct a bijection between the two. So let's define a map phi from H to XH. And how are we going to define this? Well, let's send little h to x little h. And it's elementary to show this is a bijection. Let's talk our way through it. So why is this map onto? Well, if we take an arbitrary element on the right-hand side, xh, well, yeah, it has a preimage, h. So that's why it's onto. Why is it 1-to-1? Well, suppose that phi of h1 equals phi of h2. What does that mean? That means that h1x equals h2x. Well, let's multiply both sides by x inverse on the right. And now we get, h1 is h1x x inverse, which is h2x x inverse, which is h2. Thus far, we have established the following. For any subgroup H of G, the left cosets of H partition G into subsets of equal size. The right cosets also partition G into subsets of equal size, but these partitions may be different. Now, we didn't prove it for right cosets, but the same proof works. Basically, hold it in the mirror. And also, we're making no assumption about G or H being finite or infinite. So this is going to hold for infinite groups as well. Let's compare these two partitions for the subgroup H of D4, which we started this lecture with. So here's H, and I'm going to put them in a non-standard order because I want to group the two left cosets that are right cosets together. H, R squared H, RH and R cubed H. But then the right cosets are a little bit different. These two are the same, but now it partitions these four elements like this. Notice that I've preserved the position of the elements. So RF equals FR cubed, and R cubed F equals FR. This leads to a definition. The index of a subgroup H of G, written like this, we just say the index of H and G, even though we use brackets and a colon, is the number of distinct left or equivalently right cosets of H and G. A classic theorem due to Joseph Lagrange says that if H is a subgroup of a finite group G, then the order of G is equal to the index of H in G times the order of H. So several comments. First of all, we're assuming G is finite because otherwise there's not much to show. Infinity is going to equal infinity. We either have infinitely many cosets or the cosets have an infinite size or both. Also, we've already proven this by showing that for any subgroup H, the left cosets partition the group and they all have the same size. That means that the size of G is the number of cosets times the size of each one. Here's an important result called the Tower law. If G is a finite group and K is a subgroup of H, which is a subgroup of G, so sometimes we say a chain of subgroups, then the index of K in G is the index of H in G times the index of K in H. Here's a proof by picture. What is this really saying? If we have a subgroup H, so G is partitioned by the cosets of H, but also H is partitioned by the cosets of K. So the left-hand side just says the index of K in G is the number of these small boxes, cosets of K in G, and that's equal to the number of columns times the number of rows. Well, the number of columns is just the index of K in H. You can see that here. And the number of rows is the number of cosets of H, which is the index of H in G. Now, I said finite group here, and like for Lagrange's theorem, this is going to hold for infinite groups. I'll let you explore that, but many times it's trivial. Like you have, if one of these things is infinite, then the other side is going to be infinite as well. But you could also have a case where G is infinite and all of these indices are finite, and it's still going to hold. The formal algebraic proof of this is arguably even simpler than the visual argument that I just made about counting boxes. You just plug it in. So the right-hand side, the index of H in G by Lagrange's theorem, that is equal to the size of G over the size of H. Then the index of K in H is equal to the size of H over the size of K. And so what do you notice? You just cancel the order of H's and you get the size of G over the size of K, which is, by Lagrange's theorem, the index of K in G. And that's the left-hand side. Here is another way to visualize the Tower law, but this time involving subgroup lattices. Here's the Cayley graph of the dicyclic group, Dix6, and its subgroup lattice that we very briefly saw in the previous lecture. So it can be helpful to label the edge between two subgroups in a lattice with the index. So this 2 means that there's 2 cosets of this subgroup in that one. And this 3 means that there are 3 cosets of this subgroup in that. The Tower law says that if we have one subgroup K contained in H, then the index of K in H is just the products of the edge labels from any path from K to H. So for example, if let's say that H is just the entire thing, because this isn't really big enough to properly illustrate this, and K is down here, then what's the index of K in H? Well, we just take any path, say here, and we just multiply those edge labels. So 3 times 2, or alternatively, 2 times 3. Let's now turn our attention to abelian groups. In any abelian group G, left cosets and right cosets coincide. Well, why is that? Well, the left coset xh is just the set of products of the form x times little h. But if G is abelian, then we can swap the order and write that as little hx. And by definition, this set is the right coset hx. So, in other words, xh equals hx does not imply that xh equals hx, but the converse does hold. So if elements commute, then the cosets commute. In abelian groups written additively, like Zn and Z, left cosets are written not as A times H, but as A plus H, because that's the binary operation. So this left coset is the set of all sums of the form A plus little h, where little h is in the subgroup. Let's do an example. If G is the group of integers, then the cosets of the subgroup H equals 4Z, that is the multiples of 4, are the following. There's H, the multiples of 4. There's 1 plus H. Those are the numbers that are congruent to 1 mod 4. And then there's 2 plus H and 3 plus H, respectively. Notice that these left cosets are equal to the right cosets because A plus B equals B plus A. Note that we could still write something like 3H, but that would not be interpreted as a coset. It would be interpreted to mean the subgroup 3 times H, which is 12Z. Here's a picture of a different abelian group, Z3 cross Z3, and you can see why left cosets and right cosets are the same. So the left coset of this subgroup H with this representative is 1, 0, and then follow the blue arrows. Whereas the right coset, you first follow the blue arrows, and then you follow the red path from each one. And notice how these 3 nodes are the same as that. It's just a visual interpretation of what we did up here. I said in the previous slide, be careful because an equality of cosets, xh equals hx, as sets does not imply an equality of elements, x little h equals little hx, for all elements in H. We saw an example of this in the beginning with the subgroup N of D4, but here's another one. This is one of the Klein 4 subgroups. And here it is, 1 R, F, R squared F, and then the other left coset, well, it's the other 4 elements. You can do the visual interpretation. You can go to R and then follow the paths in H, which in this case are follow blue and green, however you want to. So R, so you can see this is RH, but that's the same thing as if you start with H and then you follow the R path from everything. So from here you get that, from here you get that, from here you get that, and from here you get that. So this is HR. But there's another reason why these cosets left and right have to coincide. You see why it is? And we know that the cosets are the same size and they partition the group. And one of the cosets is H. What's the other left coset? Well, it's everything else. There's no choice. This has to be the other left coset. But since the right cosets partition the group, then these 4 elements have to be the other right coset as well. There's no other choice. We have just proven that if the index of H in G is 2, then both left cosets of H are also right cosets. In other words, using terminology from the beginning, that means the subgroup H is normal. We'll learn all about normal subgroups in the next lecture. Recall that equality of left and right cosets of H does not imply that X commutes with every element in H, but the converse does hold. So if the elements commute, then the left and right cosets are the same as well. Even in a non-abelian group, there may be elements that commute with everything. And this leads us to an important definition that we will see throughout this class. The center of a group G is the set of all elements that commute with everything. We write this as Z of G, and it's the set of little z in G such that GZ equals ZG for all elements little g. The notation Z comes from the German word das Zentrum. If little z is in the center, we say that little z is central in G. Let's think about what elements commute with everything in the following groups. So in D4, the center is generated by R squared. So the identity and the 180 rotation commute with everything. In D3, only the identity commutes with everything. There is no 180-degree rotation in Dn if n is odd. What about the quaternions? Well, we know I, j, and k and their negatives do not commute with each other in general, but -1 commutes with everything. What about the Fries group? Well, in the first Fries group, where we had every possible symmetry, the center, the thing that commuted with everything was the vertical reflection. Remember that? So if you have a Fries, and you say it looks like something like this, then that vertical reflection, so you flip it across this way, if you reflect and then translate, that's the same as translating and reflect. The horizontal reflection, that is the reflection, so when I say the vertical reflection, I mean across the vertical axis. The horizontal reflection across a vertical axis, that does not commute with everything. It doesn't commute with a translation, for example. Okay, what else? The symmetric group S4. No permutation commutes with everything except the identity itself. I'll let you, if you want to take 4 coins in front of you and play around with it and think about it, you can, but it's also not too hard to write out algebraically. And similarly, there is no element in A4 that commutes with everything as well. So, other than the identity. So these generalize. Z of D, the center of a dihedral group D2n, so symmetries of an n-gon where n is even, is also going to be the same. And similarly, if we have a dihedral group Dn where n is odd, we'll also get a trivial center. And same thing with the center of the symmetric group Sn, where n is at least 4, and the alternating group An, where n is at least 4 as well. We got to be careful when n equals 3, this holds, but when n equals 3, the alternating group is just 3 elements, so it's an abelian group, isomorphic to C3. Clearly, and I'm a little nervous to say that because if you don't see it right away, I'll explain it, so it will be. If H is a subgroup contained in the center, so if everything in H commutes with everything in G, then I claim every left coset of H is a right coset. Why is that clear? Maybe I shouldn't have used that word, but let's write it down. So what is XH? That is the set of all XH where little h is in big H, right? That's just the definition. And if we say the subgroup H is central, then we can just commute those elements. And that's the definition of the right coset HX. Okay, are you okay with me and clearly now? Okay, let's move on. Let's finish by proving that the center of G is always a subgroup. So let's think about why it contains the identity. Remember, we have to show 3 things. So let's take the identity and notice that the identity commutes with everything in G. And that's what it means for the identity to be in the center. Okay, what about inverses? What do I mean by inverses? Let's take something in the center. Let's take Z in big Z of G. I'll just say the center of G. What do we have to show? We need to show that Z inverse is also in the center. How do we do that? Well, what do we know? Let's write down for any element in G, we know that Z commutes with it. ZG equals GZ. So let me box that. So now what? Claim that if we take this and multiply on the left and the right by Z inverse, we're going to get what we want. Let's see. So ZG, give myself a little bit of room, equals GZ. So let's multiply on the left by Z inverse. We can do that, right? Then on the right by Z inverse. And what happens? Well, that cancels, and that cancels. So we get Z inverse G on the right and G Z inverse on the left. And that's exactly what we wanted to show. Therefore, Z inverse is in the center. We took an arbitrary element and showed that it commutes with Z inverse. Okay, what about closure? So what do we have to do? Let's suppose that Z1 and Z2 are central. We have to show that their product is central as well. So how do we do that? Let's take any element in the group, call it little g, and we need to show that Z1, Z2 times G is equal to G times Z1, Z2. And what do we know? We know that these individual elements are central, so I can write this as Z1 times Z2G, right? And I can pass G through Z2 because Z2 is central, so Z1 times G Z2. Now I can use parentheses to association to write that this is Z1 times G. So I've just used parentheses here. Now I can write this as G Z1 times Z2, and now using, changing the parentheses around is G times Z1 Z2. And that's exactly what I wanted to show. So thus, well, I already said check, but thus Z1, Z2 is central. Now, one quick comment. I proved the one-step subgroup test in the first lecture of this section. And let's talk about if that makes this thing any shorter. So remember the one-step subgroup test is take Z1, Z2 in the center and show that Z1, Z2 inverse is in the center. If we can do that, then we don't need to show these three things individually. So let's talk about how that would go. So if we take two elements that are central, how do you show this is central? Well, you have to basically mimic this. Z1, Z2 inverse times G equals, and then you have to end up with G times Z1, Z2 inverse. But to do that, you have to show that G commutes with Z2 inverse, not just Z2. And to do that, we really have to show this property, which is show that if Z is in the center, then its inverse is in the center. So, and I think technically to do that, what we're using here is that the identity is central. So in this case, it's not really a shortcut to use the one-step subgroup test. In other words, well, we can do it, but we can do this step, but we have to do these other two steps in the process. So it doesn't really save us any time, but there will be cases when the one-step subgroup test really is just as simple as doing closure. We don't have to do either of these. Okay, that brings us to the end of the lecture. And the next lecture will be about normality, normal subgroups, and normalizers. So the idea behind this is we saw that for a subgroup, H, the left cosets and the right cosets partition the group, but those partitions are different. And I colored the left cosets that were right cosets blue. The normalizer of a subgroup is the union of the blue cosets. It's literally the left cosets that are the right cosets. And when a subgroup is normal, that means the normalizer is everything. And normal subgroups and normalizers will be key objects that we'll use for the rest of this class. So stay with us.